the distance between the current state to the goal state is very close now, and then I know where to go. Okay, don't worry, we will cover more in details what I mean by the biases and the resistors. And throughout these topics, although it has only 19 pages, 19 slides if not mistaken, yeah, that is 19, 20, we have plenty of information and plenty of things to cover in this topic. So I hope that you can pay attention, because definitely there will be one or two questions out from this topic in either in the midterms or in the final. Right, so you have to pay attention, like how we will try to explore or perform the search from the perspective agent. It's not from our human perspective, it's from agent perspective, how the agent actually perform the move. Right? We know, we look at the map, we know that okay, you have to move this, move that, around the goal. But you have to always remember, machine doesn't like a human. Right? Machine have to follow a certain algorithm instruction to arrive the goal. Okay? Alright, so throughout these topics, we will cover only uninformed search, which is also known as a blind search, sometimes it's known as the pattern search. Alright, and we will cover a little bit on how we assess the performance among 2 or 3 different algorithms, right? How good in terms of the completeness, how good in terms of the optimalities and the others, and how are we going to assess this performance. Okay, so we have 2 main search as I mentioned. Chapter 3, we will cover the informed search, as known as the blind search. Okay, blind search means that there no information is given. Although in a map here the distance is given, but we are not going to use that information in uninformed search. Alright? Informed search, yes, definitely we need the additional information for the agent to perform the search. Okay, so that the agents know that, hey, okay, so I at this station, alright, so I'm quite far from the goal. So how to know that I'm quite far from the goal? The agents, so that you actually need to use the distance to do some calculations, alright, and then you will continue to move to the next station and calculate again. So how far me from the destination and continue to move. Right. So this stage we need information, for example the distance. So this one, no information is required. Although the information is given in the questions, we are not going to use that information. That's what is known as uninformed search. No information to perform the search. As simple as that. Correct. So we have quite plenty numbers of the uninformed search in the markets here, but we will mainly focus on these 2, black search and the depth search. So you will see that like that we use search, iterative deepening, depth search, bidirectional search, and many other search in the Google, but this actually is just a variation or the improved version from these 2 main search here, is known as the breakfast search and the breakfast search. If you can understand the breakfast search, how it works, and breakfast search, how it works, then there's no problem for you to understand this remaining. So what we won't put much time on this remaining search, we will just focus on the breakfast search and the breakfast search. Okay, so let's start with the breakfast search. Okay, so before we move on to the algorithms here, what does it mean by this word called BREADT? What does it mean by this word BREADT? What does it mean by this word? If you can understand this topic, then you know already. You don't need to look at this algorithm. If you look at this, you can understand this meanings of this algorithm means. You don't really need to look at algorithm anymore. What does it mean by BREADT? You can just Google and try to find the words that you can understand it. Yeah, Google and type this word BREADT and see what is the synonym given by the Google or any dictionary. Yeah, searching. Okay, very good. Distance from side to side. Right, so what's mean by this word? Distance from side to side. Very good. So any other words that you found from the internet? Besides distance from side to side. Width. Okay, very good. So we have other meanings like the width. Right, so what does mean by the distance from side to side? So in other words, it means that you are able to perform the search from side to side. Or level to level, right? Level to level. So you are able to perform the search. The agents, we're talking about we means agents. the agent will perform the search from site until site. If there's no solution, then only you will move down another level. Again, perform the search from site to another site. If no solution, move to the next level from site to site. So that's why you look at the algorithm here, begins with the root node. Root node means that the starting point. So let's say now we have point A here. Okay, then examine, when you look at the algorithm, point 2, examine all the nodes, each level before moving on to the next level. So it means that you search this level first. Is it equal to go? No. Then you will go to the next level, like search. Okay, is it go? No. Search. So from site to site, search. Okay, search. Okay, search. If there's no solution, we go to the next level, search again. Search again. Okay, search again. Search again. Until it found a solution. So that's why it's known as blind search pattern search. Do we need information like distance? Not necessarily. Right. So we just perform the search from the left hand side to the right hand side, no solution, go to the next level, from the left hand side to the right hand side. That's it, as simple as that. Okay? Okay, so this is one of the examples here. So let's say now you have a very simple state space. You have 8 nodes here, 1, 2, 3, 4, 5, 6, 7, 8. Okay, you have 8 nodes here. So now I'm going to perform here. Normally we have a 2 types of solutions. It's known as the early go test or late go test. Okay, so allow me to how to use Okay, so assuming that you have a very simple question here, a very simple state space here. Later on, we have one more complicated state space, and I will show you how agents actually perform the search from their perspective. Okay, so in the coding, so usually we are going to create 2 lists here. We are going to create two arrays. Right, so we are going to create 2 arrays here. So one is known as the open list. Okay, one is known as the closed list. So just assume that this open and the closed, they are just array. Okay, just array here. So the open is actually the array that is storing the node that's going to expand. So this is the array that is going to store the node that is going to expand, and the closed is store the node that's already expanded. Already expanded. So we have two arrays here. Okay? And then in the breadth search, there are some rules here. So the new node will always append behind. So, okay. And then we have to always check if the node is already in either open list or the closed list. It's already available in the open and the closed list, then we won't do the expansion anymore. Remember, in the search we want to avoid repeated states. If the node is already in the open or the closed list, then we are not going to repeat the same state again. I will show you an example. Okay, so let's take it as the early go test. Yeah. We have the 2 algorithms here. Let's say we assume that this is the early go test. So how it actually works? So let's say the goal is number 8. Right? We want to start from number 1 and arrive at number 8. So how this works? So normally the agents will start with node number 1 here. Right? So this node number 1 is not yet expand. So means that we are ready to expand here. So the agent will actually store number 1 inside the open list. So there's only 1 node here. So the agent will start to do the expansion. Expansion means that explore, search. Okay, so the moment that it searches the number 1, so this 1 here will store inside the closed list. Remember what is meant by the closed list? Is the node that already expanded. So the moment we expand 1, so we have 2 and 3 here. Right? So we have 2 and 3 under 1 here. So it will generate 2 and 3. So these 2 and 3 are the nodes that under 1 and ready to expand. So since 2 and 3 are ready to expand, then we are going to store 2 and 3 here. Alright. Okay, so what do you mean by early go test? Early go test is a test, it will check the child root. It will check the child root. Is any one of the child root is equivalent to the goal state or not? It will check this list. Do we have 8? Because our goal is 8, right? So do we have 8 inside this list? No. If no, then the agents will continue to search. Start from the left hand side, expand 2. Alright, so expand 2 here. So 2 we have 4 and 5. Look at the map. Under 2 we have 4 and 5 here. So we will have 4 and 5. So where to add? So whether we add front or the back. So for practices we append. Append means that we add from behind. So we have add from behind at 3, 4 and 5 here. Okay. So which node to expand? Look at the open list here. Okay, expand 3. Under 3 we have number 6. Okay, so 6 we add inside behind the open list. So again we check out, we have to always check, do we have number 8 inside the open list? As long as there is no goal state in the open list, the agent will continue the search. Okay, continue the search from this state, from number 4. Okay, from number 4, there's any solution here? No. So this is actually not as dead end. Okay, so no solutions. You will continue number 5. So you will continue number 5 here. 5 we have 7. 5 expand, you will get 7 here. So we will append here for 5. 4 already no more. 5 also no more. So we have 6 and 7. Okay, so again check, do we have 8 inside the open list? No. Alright, continue to expand number 6. Alright, so number 6 we have 8 here. Okay, so we have 7 and 8. So you see, 8 is already inside the open list, right? So this is the goal state. So the agent will just stop here. Then we found the solutions. So this is early goal test. It means that we will just check whether there is the goal state available in the open list. That's it, as simple as that. So it will click to array here. Then it will click expand. So it will, the successor will just store inside the open list and check, do we have the goal state inside the open list. So from here, what is the search part? From here we get 2 information here. How the agent perform the search. The agent start to search from 1 to 2, search to 3, search. Okay, so stop already. So this is the goal. Okay, so this is the first part. It's not 1, 2, 3, 4, 5, and 6. So this is the first part. Right. So what is the return path? Return path is the path that the humans will need to travel. Right. First part is how the agents work. So this is more toward back ends. Return path is the front ends. Right. What are the stations that we as a human we have to travel so that we can arrive destination in a more effective way. So how to find the return path is the path that joins the initial state to the goal state. So this is your return path. So you have 1, 3, 6, 8. So it means that as a user, we just need to travel from 1, travel 3, travel to 6, and travel to 8. So this is our goal state. So this is how the agents perform the search. And the whole process here is how the agent actually perform the search in the coding. Okay, so from the agent's perspective. Right. So this is early goal test. So now let's try again with another algorithm. It's known as late goal test. Okay, so I'm going to repeat again one more time. Okay, so now we start with the late goal test. So early on, so this is the early goal test. So this is actually early. So now let's try with the late goal test. So late goal test is a different than early goal test. Late goal test, we will check the parents nodes. Or in other words, we will check the closed list. So early on, early go test, we check the open list. Okay, as long as one of the child node is equivalent to the go state, the agent will stop. Let go test is, we will check as long as the node that's going to expand is equal to the go state, then we will stop. Yeah. So there's no wrong or right, so both algorithms are correct. Yeah, both algorithms are correct. So again, so let's create two arrays here, open and the closed list. Okay, we will start with the node 1. So node 1 at the open list. So now there's only one node, so we expand number 1. So the moment we expand number 1, we have two successors here, 2 and 3. 2 and 3. Right, so we have 2 and 3. And in this case, we will check this one. We will check. Right, instead of checking the open, we will check the close. So 1 is not a go state, so the agent will continue to search number 2. So if you search number 2 here, it will generate 4 and 5. 4 and 5. Alright, so we will append behind. Alright, so 2 is not a solution yet, so we will expand 3. So the moment we expand 3, we will get 6. So again, we have 4, 5, 6. So again, there's no solutions in the closed list, so we will expand number 4 here. So for there's no solutions, again dead end. Alright, so continue number 5. 5 you will get 7. Okay, so we have 6, 7 here. Okay, so there's no solutions yet, so we expand 6. 6 you get 8. So since this is let go test here, right? So we are not going to stop because there's no 8 in this list yet. So we will continue number 7 first. Okay, 7, that end. No solutions. Okay, 8 expand. Yeah, so the moment the 8 put inside the closed list, yes, so the goal, this is the goal. So the agents will just stop here. So you can see that the solutions for this both are the same. But this solution, this space, you get the same state, search tree or the path, or so-called the tree here. But there is some questions where you will get a different tree. Alright, so again, so what is the search path? Search path is from 1, the agent will search number 2, search. Okay. So this is the search path. And what is the return path? It's the path that starts from the initial state to the goal state. 1, 3, 6, 8. That's it. Okay, and this one is known as search tree. So this one is known as search tree. It's just an illustration to the user how the agent is actually performed the search. So the only difference here is the search path. Search path you see here is 1, 2, 3, 4, 5, 6, 7, 8. But using the early go test, it's only 1, 2, 3, 4, 5, 6. Finish. Yeah, it's different. But the return path both are the same. Is that okay? Okay, so don't worry, we have one more questions to practice later on. Okay, so we may see that the pattern search for the preferences is pretty simple. We will actually start from here. We search here. Next no solution. We search here. Okay. So yeah, so one of the child nodes from the 6 is solution, so we will stop here. So since we are using the let go test, right, so we will start from here. Okay, search, okay, there's no solutions. Okay, horizontal, right, from side to side. From side to side, no solutions. Okay, from side to side. Okay, so there is a solution here, so we will stop. So this is references from side to side. So information, no need information. Do we need distance? No need. Do we need time? No need. Just based on the pattern. Okay, a very simple state space, then you can use the blind search. Okay, is that clear so far? Good. Okay, so you can see the child, the brain is there. Yeah, so there's a, well, start from 1. This is search, 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 search. Okay, in horizontal manner. Okay, so let's do a simple exercise here. So using early go test, let's say we use early go test here. List the sequence of the search path and the return path if we use breadth search. Okay, so what is the solutions for this case? Yeah, if we use early go test. So what will be the search path? Okay, so the search path will be start from R, right? A, M, B, J, N. Then one of the successor is equivalent to the goal state. Then we will just stop here. So this using early go test. We check the child root. Yeah, as long as one of the child roots is equivalent to the goal state, then the agent will stop it. Okay, so what is the return path? The path that joins the initial state to the goal state. R, M, and O. That's it. Okay, alright. So how about using, okay, shall we move to the next slide? Okay, good. Okay, how about this? So this one is using the let go test. Okay, so let go test is check the parents node. Yeah, we need to check the parents node. Is it equal to the goal state? If not equal, then we will continue the search. Right, so for this case, we will start with the R first, right? So we start with R, search. Right, to return it. R, A, M, B, J, N, P, C, K, O. Right, so it will search, okay, no, search, search, no, search, 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 search. Okay, I do this, that's equal state, yes. Right, so what is the return path? Return path is exactly same like the early go path. Right, so we have Rn and O same. And the only difference will be the search path. Will be slightly longer compared to the early go path. Good. Yeah. Everything is right. Okay, so let's try with a more difficult one. So let's try these questions. Let's try these questions. Okay, more difficult. Okay. Okay, so let's try it together. Okay, if this is too small, then perhaps you have to look at the slide. Right. So let's say now we are going to use a legal test. Yeah, a legal test. Yeah, a legal test. Okay, so this so-called the state space is a directed graph, right? So means that A can travel to B, but B cannot travel to A unless you have both directions here.
Oh my word.
But if you know that, you have to like fix this one. Okay, and make sure that you travel according alphabetical order. Sometimes the question will state you, okay, so travel according to the alphabetical orders. Sometimes it didn't state. If it didn't state, it can just expand whatever you like. But it says follow alphabetical orders, then you have to follow alphabetical orders. Yeah? Okay, so let's say now we try to expand using brackets. Same things, we are going to generate two arrays here, open and close. So open and close. Okay, so we will start with A first. Okay, A.
B.
So expand. A. So make sure that goal state is J. This is your goal state here. And this is early go tag, so we will check this one. Hopefully my work is okay. Alright, so now A, moment you expand A, you have B, C, and D. You have B,
The special.
C,
Got the special.
So we put here B, C, and D. Okay, so continue. The agents will go to the list or array and expand this B. So the moment you expand B, you will have two successors here, E, F. So to know whether we have a repeated state, we just need to check whether E and F are already available in either of the list here. If E and F is not inside open or in the closed, we can put it inside here. So we expand the B, so we will get E and F here. So since E and F is not inside the open and closed, so we can just add E and F here. Okay, so we will have E and F. Okay, so continue, expand C. So the moment I expand C, you will get three nodes here, D, H, and G. Right, but however, the D is already here. Yeah, so this D is already available here. So we don't want to have repeated state. So D will not append inside. We will only add G and H. Right, so only G and H. Is followed alphabetical order. E, F, B, C, D, E, F, G, H. Yeah, so we have D, E, F, G, and H. So here we have only G and H. Okay, finish. Right, let's check. So do we have J? So this is our goal state. J inside the open list. So far we didn't see any J here. So we have to. The agent will continue to check here. All right. So continue the donkey here. D. So D, it leads you to H and I. But H is already available, right? Available here, H here. So we don't add any more. So we just add I. So E, F, G, H, I. So it means that there's only one node under the D. Okay? So continue E. E go to F, but F also already available here. So one repeated state, so no more node to expand. So this is dead end. There's no more successor from an E. Alright, so continue with the F. Continue with the F here. So F gives you K. Right, so F gives you K, so we will append G, H, I, K. Alright, so F, you have K here. Okay, good. Alright, so far it's okay. So right, continue with G. So if we expand the G, so we will have F and J, right? So F already here, so we don't put. So we have H, I, K, J. So do we have J? Right, so the J is here already. Right, so this is our goal. So as long as the goal is already in the open list, which is in the child's loop, so the agent will just stop. The agent will just stop here because it found the goal. So this will be the search tree. This is the search tree for the agents. And what is the search path? The search path just need to follow the closed list. Right, so agents will start to find B, A, B, C, D, E, F, G. So what is the return path? Return path is the path that joins the starting point to the goal state, which is A, C, G, J. A, C, G, J. That's it. Okay, so this is the solutions for these quite complicated questions. But you have to always remember, although the state space here, we have this information. So this is in distance. But as I mentioned earlier, blind search, we don't use distance. We don't use information. We just perform the search based on the pattern. Okay, so this is early goal test, where as long as one of the nodes is in the successor, then we will stop. We will stop. Okay? So let's try continue with the late goal test. So let's say we try to continue, we continue with the let go test. I'm going to use it using the green color here. So in the let go test, we are going to check if the closed list here having this node called J. Right, so now we are going to continue. Right. So let's say now I'm going to continue. I'm not going to withdraw another tree, so I'll just continue with this tree here. So let's say now I'm going to continue with H. Okay, H. Okay, if you look at H here, so we have only L and G. GL here. So G is already available, so we have only L. So we put L here. Okay, so we put I, K, J, L. Okay, continue with the I, you go to L. Right? You look at the state space here. I, you can go to the L. So L already in the open list. So we don't have any repeated state. So we put I. So this is that end. That end. Continue with the K. If we continue to K, K can go to G. Again, G already repeated, so we don't put. Okay, so again, so this one is that end. Okay, expand J. Okay, so J is the go state, so we stop here. So if you use let go test, so this is another substrate, so represented by the green. So you have one more node here, so this is the let go test. Okay, and the search tree, and the search part will be definitely longer. Right, so this is the search tree for the let go test. Is that clear? Yeah? Very simple. A let go test, we check the successor. Is it equal to the go state? Let go test, then we just check the parent space. If the parent space is equal to the go, then we will just stop it. Okay? So, any questions for this simple example here? Right, so if no, then let's move on. Okay, so if any questions, feel free to go to the tutorials. We have plenty of questions. Yeah, so we have a very good question in the tutorial, so we just practice using the early or the late, and if you have any questions, consult your tutor. Okay. So this is breakfasts. Breakfasts from side to side, right? So, and the example I showed you just now, so this example I showed you just now is from agent perspective, from the computer perspective. So the agents will actually store all the nodes inside the array. But if inside, during the expand, if you feel that you already good in expanding, you don't need to have, you don't need to show this, the open and closes actually. And the open and the close is just to let you know to understand how the machine is actually store the nodes and expand the tree. But if you're already good, just show the tree, then it's good enough. Okay, so this one is optional, it's not necessary. Alright? Okay, so let's continue with the another algorithms here. It is known as depth first search. Okay, so again, so what do you mean by depth? D-E-P-T-H. So what does it mean by these words? Depth first search. When you have to search, what is the synonym for this word called depth? Yeah, simpler. Have to find what is meant by this word depth. Distance from the top to distance from top. Okay, so distance from top maybe to the bottom. Okay, so meaning that any other words? Vertical, do we have a word called vertical? you can see that the breakfast search is different from mistake. Breakfast search is from top. Okay, search to next level. Yeah, search to the next level. And although there is a note at the left hand side here, yeah, we don't check this. The agents will prioritize the nodes at the branch, at this branch. Continue the search. If there is no solutions on the back end, then only the agents will travel back and try to explore the node beside same levels. Okay, if let's say no solution, backtrack. Okay, backtrack. If no solutions here, backtrack, then only will expand from this direction. Okay, so this is the difference between the breakfast search and the depth search. Breakfast search from side to side, level to level. Depth search level to level first, then side to side. Okay, alright. So if you look at these algorithms here, always expand the deepest nodes in the current freeze. Current freeze means that the branch, current freeze, and this is the freeze, it's actually the branch. Yeah, the nodes leading from that end normally will be discounted from the memory. So back to the next levels nodes that have yet unexplored successors. Okay. Alright, so you look at how it actually works. So you have ones, actually number 2, number 3, okay, no solutions, number 4, number 5, back, 6, 7, 8. Okay, so now let's explore from machine perspective here. Okay, so in this case, we normally use let go test. Normally we use let. Normally we have to use let go test. Okay, so see, so the moment that agents would like to explore using the breakfast search, two array will be created, open and close. Okay, so how to know whether there is a repeated state? You still remember in the breakfast search, right? In the breakfast search, we will check both. We check both. Do we have any nodes within or inside open or closed? If yes, then we avoid repeated state. Right. But in the breakfast search, we will just check the closed list to avoid repeated state. Okay, so means that in the algorithms, you just need to check do we have a node already available in the closed list. If yes, then we don't put again inside the open list. If already inside the open list is okay, you can just re-put again, no worry. Okay? Okay, so right, so normally we use a let go test, means that we are going to check the close. We have the go state inside the closed list here. Alright, so we are going to start with the number 1. Okay, so explore number 1 here. So the moment you explore number 1, you have 2 and 6. Okay, you have 2 and 6 here. So we have 2. So we always start from the left hand side. So 6 although is a successor from 1. So normally what I will do here is I will put a dotted line instead of a solid line. So why? Because you have to always remember that process is a focused prioritized branch. Branch from the left hand side. Then if no solution, go to the left hand side, go to the neighbor's successor, which is the same levels. So therefore, I put a dotted line, so that means that I'm not going to prioritize with this branch first. I will just focus this branch. So how to add in front? We will add 2 and 6 here. Okay. Alright, so we check do we have any number 8 inside the closed list or not. If no, explore number 2. Okay, so we explore number 2, we have 3 and 4. So we have 3 and we have 4. Okay, so 3 and 4, so just not breakfast we add behind. So here we add in front. We add 3, 4, 6. There's a difference between the breakfasts. The breakfasts we add from the back. We add from the back. But the breakfasts we add in front. Yeah, we add in front. Yeah, 3, 4 we add in front, we add from in front instead of a parent. But if you have 3, 4, 6 here. Okay. Okay, then we expand number 3. So number 3, there's no more successor here, right? So this is actually a dead end. So with that end, then we actually do backtracking. Right? So backtracking, expand number 4, which is this one. Then it becomes a solid line. Yeah? Expand number 4. So expand number 4, you will get number 5 here. Right? So number 5 is not available in the closed list, so we can just put it inside here. 5, 6. Okay, 5 expand. Expand 5, no solutions here. Right, so again, so this is that end. Right, so no solution, okay, backtrack, okay, backtrack. Okay, then now only number 6. Then only number 6. Right, expand number 6, you will get 7. Okay, expand 7, you will get 8. Expand 8, yes, finally, number 8 are available in the closed list. So this stop. So you can see that the search is totally different compared to the previous search. So this one, the search path. You will compare to the previous one. The search path for this case is 1, 2, 3, 4. This one is 1, 2, 3, 4, 5, 6, 7, 8. Okay, and the return path, same 1, 6, 7, 8. Okay, so let's compare with the practices. So this one is a practices. Oh, okay, I think we use the we use a different state space here. So you can see that if you use the same state space, the values here will be different. Okay, so remember, so this one we search. Okay, no solution, search this branch. Okay, no solution, backtrack, search this solution, this branch. Okay, a very simple example using let go test. Is that clear? Okay, so let's move on to the more another questions, which is this one, so more difficult one. Okay, so we will apply the same dataset apply onto this graph. Okay, so let's start now. Alright, so since we are going to treat the two array, open and the close. So this is dataset using let go test. Okay, start with A. Okay, start with A. So A expand. So you get B, C, D. So we have B, C and D. Remember, so I put a dotted line because we didn't explore. We just stand by. Yeah, we just stand by here. Right. So we just put a dotted line. So we have B, C, D. Okay. Always start from the left hand side. Explore B. Explore B. You will have E, F here. So you have E, and you have a dotted line. Alright, so we add in front. We add in front here, so we have E, F, C, D. Okay, we have the F, C, D here. Right, so explore E. Explore E, you will have F. Right, you have F here. As I mentioned, although this is F, which is all available in the open list, but we check the closed list to avoid repeated state. Right, so here we can still put the F here. So I can put F which is start from the E. So this one we have another F. So this F here is start from the B. Yeah, so no problem. Yeah. So we check this one for repeated state. Okay, so we expect f. So we expect f equal to the k. So this one should be 1f here. Alright, so f equal to the k. So you have 1k here. Okay, k expect go to the g. So g. Okay, g as pro you get j or f, right? F or j here, but f already here, right? So we don't want to have a repeated state. So j, f, c, d. Okay, and then f pro j. So those there. So stop here. Right, done. So this is the search tree for the depth search. And what is the search path? A, follow the closed list, A, B, E, F, K, G, J. What is the return path? For this case, same like the search path. Done. That's it. So this is the search tree for the depth search. Totally different than the graph search. It's totally different. Yeah, graph search we search horizontally. Depth search we search vertically. We search vertically. Okay, so we will take a rest for 10 minutes. If you have any questions, still not sure how the practices or practices work until this point, feel free to come down and discuss with me. So we will come back in 10 minutes for another example.